Anyhow, so before we get started, I wanted to let everybody know there is a question of the week posted. I honestly, right off the top of my head, couldn't tell you what the deadline for that is, but there is a question of the week posted. I think I gave y'all till Sunday just because of the weather and everything else. Having said that, before we really get into all this stuff, what can y'all tell me about continuity? What do you think continuity is? Folks at home, what do y'all think it is? Awesome, quiet stoicism for the win. All right, so continuity is really just the idea of, is your graph continuous? So the question then becomes, well, what does it mean for a graph to be continuous or a function to be continuous, right? Like, how can a function be continuous or how can it be discontinuous should be the question, right? Well, one way to think about continuity is straight up just looking at the definition, right? The definition of continuity, if our function is defined at a point, if the limit at that point exists, and if your function at that point and the limit of your function at that point are equivalent, then we say our function is continuous. That's all well and good, but definitions don't give us an intuitive understanding of what this means, right? Like, we can look at this and be like, cool, great. What does that mean? What that means, all of these definitions together, is that you can draw your graph without ever lifting up your pen or pencil. This is one way we can think of it in an intuitive sense. Okay, well, let's go back to these definitions for a second and see why that is. The first thing we might note is that if our function is defined at C, there's two different possible cases we might be running into. There's actually three. We might have a case like this, right? We might have a case like this, or we might have a case that looks something like this. In all of these cases, our function exists at C, right? Like here, our function would be whatever this point value is, right? Whatever this y is. In this case, it's just whatever that would be, right? In this case, in this purple case, it would be this point here, 0. So we can say, in all three of these, our function is defined at C. Okay, well, if we go with just the second definition, or just the second part of the definition that the limit exists, you might have two different cases. You might have this case, or you might have this case, right? Our limit would exist here, and our limit would exist here. Agreed? So these first two cases, notice that there's always a hole that could possibly appear. That one of the possibilities leaves for a hole. And we don't want that hole to be there. So this final case, it just says that the two alone aren't enough. But together, you're left with just this possible case. Does that make sense what I mean? Yeah. And in that way, we can think of continuity as a description of our ability to draw the graph of our function without lifting up our pen or pencil. Is everybody with me so far? Yeah. So, as a couple cases of types of discontinuities mixed in with continuity, Notice our graph is discontinuous here, it's discontinuous here, it's discontinuous here. Now, when we talk about discontinuity, something that is worth noting on paying attention to is the fact that we talk about discontinuity in terms of points. But we talk about continuity in terms of intervals. Our function here is continuous from C3 to B, not including C3. Our function here is continuous from C2 to C3, not including either of those points. But our function is discontinuous at C1, C2, and C3. Another way, well, I'll get to that in a second. Having said all of this, it's nice to know when functions are going to be continuous and what type of functions can be linked to different types of continuity, right? Like, it's helpful to know when we're talking about polynomials that every polynomial is continuous. That's something we should know. We should be able to look at a polynomial and say, yeah, it's continuous. Rational functions, on the other hand, they're only continuous in their domain. And I'll get to that in just a second. But first, two different polynomials. So the second power to the third power, right? Clearly, these are both polynomials. Just looking at these, we should be able to tell that they're continuous, but based on that previous slide. But to convince ourselves of that, let's look at their graphs. There's never any holes in them. If we went from negative infinity to infinity along our x-axis, we would never find a discontinuity. Again, that's because these are polynomials. But with rational functions, things change. Looking at A, when would this be discontinuous? What do y'all think? What numbers aren't in its domain? Zero. So we would say that A is continuous everywhere except at 0, or that it's discontinuous at 0. In the case of B, 1's not in its domain. So B is discontinuous at 1. Now what about C? Is C ever going to have a problem with discontinuity? How about y'all play with it for a second, see what you think. Try to find the domain of C for a second. In the case of C, what we're curious about is if our denominator is ever going to be 0, right? Is there any real number that can make that denominator 0? No, right? Like x squared plus 1, the smallest it's ever going to get is going to be 1. So it's never going to have a discontinuity, this function as a whole, right? And in that way, we would say that it's continuous from negative infinity to infinity. Another way we can think of these, like I said before, is in terms of their domains, right? 0 is not in the domain of 1 over x. 1's not in the domain of x squared minus 1 divided by x minus 1. in all real numbers are the domain of 1 over x squared plus 1. All right, well, what about on closed intervals now? What if we want to contract what part of our graph we were looking at? So up here, we've got this graph, right? If we wanted to say, let's chop it up, we only care about this bit. When talking about continuity at the end of these intervals, we would use the one-sided limits. Does that make sense what I mean? We would just say, what's the limit from the left here? I mean, from the right. What's the limit from the left here? And that's what we're getting at here. So instead of using the full limit, you just use the one side that's appropriate. On your left, most part of your interval, you want to approach that value from the right. On the rightmost value of your interval, you're going to be approaching it from the left. Okay. What about here? What would be the continuity, or what would be the case that we need to worry about here? Like, how are we going to determine where this is continuous and where it's discontinuous? Well, the first thing we need to know is where this function even exists, right? Like, what is its domain? So, the domain of f of x equal to the square root of 3 minus x is going to be any value of x where 3 minus x is greater than or equal to 0, right? Everybody agree with this? So this is going to tell us then that the domain is going to be any value 3 or less. Well, hey, wait a minute. That then means that what our function is going to look like, this is going to be restricted to just the domain from negative infinity to 3. So if we want to talk about the continuity of this, we have to talk about it in terms of this interval, right? And this is the square root of a thing, so it's continuous everywhere for the most part, right? We just want to concern ourselves now with the far left end and the far right end. Agreed? Well, the far left end, we know it's going to keep going on forever. Everybody cool with that? Yeah. The far right end then is where we need to worry about. And in that case, we're going to need to take the limit as x approaches 3 from the left of the square root of 3 minus x. Well, this is going to come out to be 0, isn't it? Which is equal to f at 3. So we would say that this is continuous in its entire domain. And just to kind of convince ourselves of that, let's check out the graph. From 3 up to infinity, right? Nothing really changes here. It's the square root function just reflected and shifted. Agreed? So we're continuous from 3 up to negative infinity. Or down to, rather. Having said that, knowing different things about these functions will make it a little bit quicker for us. If we know that the square root is continuous on its domain, then all we need to do is find its domain, right? Does that make sense what I mean? And that's what they're really saying here is the square root's continuous everywhere on its domain. So all we need to do is find its domain and we can say that it's continuous on this interval. Okay, what about this? First, what's its domain? What's the domain of this piecewise function? Those of y'all at home, what do you think? Is my speaker on? Sure is. So, yeah. I didn't mean to click that. Let's go back to the slides. So I say again, people at home, what's the domain of this function? All right, awesome. Nobody at home's listening. Cool. All right, so the domain of this function is going to be from -1 to 3. Because check it out. What we're saying is this first part, we're going to do it for all of the x values from -1 up to 2, and we're going to include both of those values, right? And then the second part, we're going to do it from everything down to 2, but not including 2, up to 3 and including 3. So we're going to include all of these points, right? All of these possible x values from -1 to 3. So we know our domain right away. The next thing we're going to want to know is where is it continuous and where is it discontinuous? Well, we know this is a polynomial, so it's continuous everywhere. We know x squared minus 1 is a polynomial, so it's going to be continuous everywhere. But are they continuous where they meet? Do they meet at the same point? If we approach 2 from the right, is it going to be the same as when we approach 2 from the left? And is that going to be the same as the value of our function? Well, we know it's going to be the same as the value of our function because 2 is included in this first part. X minus 5 is a polynomial. So we know it's continuous, right? And since it includes 2, we know that the limit coming at it from the left is going to be equal to what that function is at that point. Is everybody cool with this? No? The question then is, what about coming at it from the right? To give you an idea, this is what our graph looks like. All right, so the point in question is 2. Going up, this is where we meet, right? What do y'all think? Just looking at the graph, is our function going to be continuous at 2? Yes. Yeah, because there's no hole, right? So let's verify this now. I'm actually going to write it on the board first. All right, so what we want to know is the limit as x approaches 2 from the right of f of x equal to f of 2. So this is the same thing as saying the limit as x approaches 2 from the right of x squared minus 1. Well, this is a polynomial, and we know from the properties of a limit, we can just plug in 2 now. When we do, we're going to get 4 minus 1, which is equal to 3. And it's going to be equal to f of x at 2, right? Everybody agree? Because f at 2 is going to be equal to 5 minus 2, 3. Because 2 belongs to this first part, right? Everybody cool with this? So, looking at everything, the limit from the right is going to be 3. The limit from the left is going to be 3. The limits agree, and they're equal to the function value. So we know that the function is continuous. Is everybody cool with this? All right, now, step functions. Here we're just talking about one of them, but I really quickly want to introduce all 3 of them. So there's a couple different notations we're going to see for step functions. This is the ceiling function. You round it up to the nearest integer. So if you're given 3.1 for x, this would come out to be 4. This is the floor function, and you round it down to the nearest integer. So if you're given 3.1, you would get 3 out. And this is just the step function, and it just rounds it to the nearest integer, period. Make sense what I mean? No? Okay, so as some examples. The step function of 4.6 would give you 5, but of 4.3, it'll give you 4. The floor function of 4.6 will give you 4, and of 4, well, it rounds it down to the nearest integer. The nearest integer to 4 is 4. And the ceiling function of 4.6 rounds up to 5. And of 4, well, it's going to round it up to 4 because its nearest integer to 4 is 4. Is everybody cool with this? Now here, they're talking about the floor function. So another form of notation that we'll see is this double bracketed square thing is equivalent to this. So this is all well and good, but what does this thing look like if we were to graph it? It will look like steps. So this is the graph of the floor function, right? All this thing does is says, take these steps, right? We're going to include the smallest possible first integer. So at 0, we're going to round it down to 0. And anything between 0 and 1 will be rounded down to 0. At 1, we're going to include 1. And anything between 1 and 2 is going to be rounded down to 1. Similarly, 3, 4, 5, 6, so forth, so on. Now, the reason why this is a good function to introduce now is because if you look at it, this is far from continuous, right? And this thing is great for just making functions that break continuity. You throw this into something and you're pretty much guaranteed, in most cases, to not have a continuous function. So in that way, we're going to be playing with it. We're going to say, all right, I want a function that's discontinuous. Why do I inject this thing into it? Make sense what I mean? So if you ever see the step function, assume there's going to be discontinuity somewhere and go searching for it and go looking for it. As an example, this thing. So this thing here is going to take steps, right? It's going to be like adding integer values. This thing is going to be like adding just an x value, 3 times x to be specific, but it's that type of an idea. Is everybody cool with this so far? So what do you think the graph of this is going to look like? If you had to guess, try sketching out the graph really quick. See if what you come up with is what's on the next slide. All right, so the graph of this, it's going to kind of look like the step slant function almost, right? Where like we take our traditional 3x function, right? We add these little steps in between and break it up. We break it up into discrete parts. And if we think about what's happening here, it kind of makes sense because all through 0 to 10,000, this bit is going to act like 5,000 plus 1. Agreed? Well, 5,000 plus whatever this comes out to be. So it's going to act like kind of like a constant. And then you're going to add 3x to it. And then from 10,000 to 20,000, it's going to act like another constant plus 3x. And then 20 to 30 is going to act like another constant plus 3x. And that's why you have this breakup pattern. Does that make sense? It's kind of like a bad relationship. Always breaking up. Okay, dad jokes all day. I get it. Cool. Awesome. So what do y'all think? Is this making sense so far? It's different, right? Like we're going to have to stop and really think about what we're looking at when we see this step function. But if you look, they're trying to say the same thing. That from 1 to 10,000, this is gonna be 0. So 1 plus 0 times 5,000. From 10,001 to 20,000, this thing's gonna be 1. So this is gonna be 1 plus 1, 2 times 5,000 plus 3x. So forth, so on. Yes, ma'am.
Does the 3x at the end there means, okay, if for example there was like 4x at the end would have been 4 steps, but does the 3x at the end determines the number of steps?
No, the 3x here will really determine how selected you are. What determines the steps is what's happening in here. So this is going to tell us that from 1 to 10,000, this thing's going to be 0. Because if we have 1 minus 1 is 0, divided by 10,000. 10,000 minus 1 is going to be 0.9999999. Well, that's going to round down to 0. So it's really this thing that determines the step property. This thing is going to keep its normal behavior. Does that make sense what I mean? Cool. So having said that, on this last slide, before y'all take the exam, I would like y'all to check out this last slide on your own at home, just to quiz yourself and see how well you understand it, if you have any questions. This is really here just to encourage y'all to be like, all right, what are my questions? What do and don't I understand? Make sense? And that is everything I got on those slides. So, having said that, let me get rid of this really quick. How do I remove pen? Dope, awesome, all right, cool. So, having said all of this, who saw my last announcement? Anybody? Nobody, awesome, all right, cool. New material then. Who knows what a secant line is? Anyone? No? Awesome, even better. I'm not gonna sound like a broken record. So, a secant line, well, to begin with, a secant comes from the Latin word meaning to cut. What a secant line is a line that crosses a curve more than twice, or well, twice or more, I should say. So as an example of a secant line, let's imagine we've got this curve here. I'm going to go ahead and call this a function. I'll explain why in just a second. We're going to have this curve here, this line. We're going to have that line. Of these, which are secant lines?
Probably the green one.
Well, the green one is going to be our curve. I should have started with that. So this is our curve, and these are all of our possible secant lines. Blue, yellow, orange, that we're just looking at for now. There's an infinite number of possible secant lines.
And I'd probably say blue and yellow.
Blue and yellow. Who agrees? Most of us, right? Yeah, you're absolutely right. Blue and yellow are secant lines. Now, the reason why I said the green one is a function is because in order for this to definitely not be a secant line, we need this to be a function. Because a function can't wrap back down on itself, right? So now we know this line only goes through one point. Does that make sense what I mean? So I'm really pulling together a couple of different ideas. First, what's a function? A function is an equation that, like we've said before, doesn't wrap back in on itself, right? For every x value, there's only one y value. So knowing that this green line is a function means this here is the only possible point for it. So this orange line has no chance of passing another value of our function. And in that way, we know that this orange line can't be a secant line. Is everybody cool with that? Okay, so let's say we're given a function. We want to find a particular secant line. In a second to draw this on the board. Let me make this a little bit more curvy. There we go. I want to do this. Okay. Your mission, you don't have a choice to accept it or not, is to draw a secant line, to find the secant line that goes through these 2 points. How would you do that? In other words, you want to find this line. What is its equation? Well, we could use point slope form, right? To find the equation of this line. We could say this line is equal to y minus, choose some particular y value, is equal to m times the difference between x and the x value associated with that particular y value. Is everybody with me on this? Well, we know that the slope from our previous lectures, the slope is going to be equal to our function evaluated at b minus, let me make more room. Our function evaluated at b minus our function evaluated at a divided by b minus a, right? Everybody agree with me so far? Okay, so let's step back for a second. Let's look at this graph. We know, I'm gonna erase some of this really quick. You know, this is x equal to a. And we know that this is x equal to b. What else do we know about this graph? Well, we know that we can call this distance delta x. And if that's the case, then b is going to be equal to a plus delta x. Everybody agree? Huh. Okay. Knowing this, we can rewrite some of this, can't we? Everybody agree? In particular, we could rewrite m now. I need to lay off the roll. Thank you for the chuckle. I appreciate that. It does my ego well. All right, so knowing this, we can rewrite this formula. We can rewrite it as half of a plus delta x minus half of a divided by a minus a plus delta x minus a. Or we can drop the parentheses. We're just left with delta x. Agreed? Is everybody with me on this? Okay, so when we do this, we get something that keeps showing up in our homework, which should be a pretty good hint that there was a reason for us to do that in our homework. I got somewhere I'm heading with all of this. Let's say now we wanted to fix one of these points. I wanted to hold down A and move B closer. What would happen to our line? Where a line would kind of move like this, right? Until it got to a point where the difference between x equal to A and x equal to B is indistinguishable, right? Everybody agree with that? We hold down A and we move this closer. Well, notice in that description, we're talking about a limit, right? We're talking about the limit as the difference between our points, this delta x, goes to 0. So what I'm describing, let me erase some of this now. What we're describing is the case where this thing goes to 0 and that thing moves inside, right? So we're holding our finger down, we're pulling this point closer to A. So we're sending delta x to 0. This looks like a limit, right? Looks like we're saying when we do this, when we let delta x approach 0, what happens to our secant line? Eventually, x equal to a and x equal to b, they become the same point, right? Like at delta x equal to 0, they are the same point. So our secant line doesn't go through 2 points of our graph anymore. It doesn't go through these 2 distinct points. So it only touches 1 point right there. And in that way, it turns into what's called a tangent line. Read some of this. Right, this is what happens when we let that point B approach x, or delta x approach 0. This line here is called a tangent line. A tangent line is a line that touches a curve at 1 point. And if you were to look really close at that curve, zoom in, the graph of your curve would be indistinguishable from your line. So what does that mean? It means that the tangent line has a slope equal to the slope of your curve. So your tangent line has a slope for sure, but your curve doesn't, because slope is really something we only talk about in terms of straight lines. Does this make sense what I mean? So like if we were to zoom in to this part, what we would see is this. Blue is still our function, yellow is still the secant line, and pink is our tangent line. Notice right around that intersection, you can't really tell the difference between our function and the tangent line. That's because they have about the same slope. They move in the same direction or close to it around that point, in the neighborhood of that point, which is an actual mathematical term, whether that's word. So another way, well, I'll show that in a second. What we've shown then, or what we found by using this limit, is what's called the derivative. The derivative of a function at a point. This crazy looking thing, it's called the derivative of a function at a point. Same thing, just more technically correct. Now this thing, there's a bunch of different forms of notation to represent it. The first way that we might represent it is dx f at a. We might also represent it as d f of a dx or dy dx or the subscript x f at a or f prime at a and a few other different ways we might write it. So just some notation to know about if you see any of these things, they mean the same thing. So what have we just seen? Like visually, what does this all mean? Well, I am happy y'all asked. Let me pull up a nice little GIF for everyone. Because it's GIF and not GIF. Disagree with me and I will fail you. Okay. Those of y'all at home, let me pin the tab. I don't know why I did that. Okay, whatever. That still works. Oh, that's why I did that. Okay. Come on, get there. Okay, so what all this is, what all this looks like. In blue, in this graph, what we've got. That's weird. Anyhow, in blue, what we've got is our function. The dotted red lines are our secants. Notice on one hand, we've moved delta x to the left. On the other hand, we move delta x to the right. And in this green, this is our tangent line. And as the limit, in this case of h, approaches 0, it's really our delta x. As the limit of that approaches 0, these secant lines approach our tangent line. And the slope of this tangent line, well, it's equal to the derivative of your function at that point. Is everybody with me on this? I know I just threw a lot at you really fast. Like, just went through the derivation of the limit, or I mean of the derivative of a function at a point. Just went over the secant line, just went over the tangent line. What does it all mean though? Like, what are we looking at here? What does this, any of this tell us? Well, the tangent line has a slope at that particular point. If the slope of our tangent line right here is approximately equal to the slant of our function around that point, in some sense, then what this must mean is that the change in our function is related to our derivative. In fact, it's not just related, it is our derivative. If we wanted to talk about the change in our function in the y direction compared to the x direction, we would be talking about the derivative. Is everybody cool with this? Okay. Having said that, what time is it?
6:35.
6:35, what time does the class end?
8:50.
50? Okay. So, all of this is well and good, but it doesn't do much for how to use this stuff, like what any of this might mean. So, let me turn this off. Where's my eraser? Right here. Let me erase some of this. And let's look at an example or two. All right, our first example, let's say our function f of x is equal to, somebody give me a good polynomial.
Plus 3.
All right, I like it, x squared plus 3. All right, so we want to find the derivative of this function at, somebody give me an x value. 7, all right. We want to find the derivative of our function at 7. So we're going to say the limit as delta x approaches 0 of f of 7 plus delta x minus f of 7 divided by delta x. This looks like it's going to suck, right? So let's go ahead and work on it, because that's a good problem, right? All right, so first thing we're going to want to do is we're going to want to replace all our functions with their equations, right? We're going to want to plug in 7 plus delta x in for every x of it. And it's going to look like the limit as delta x approaches 0 of for the record, the answer is going to be 14. Of 7 plus delta x squared plus 3 minus 7 squared plus 3, all of this over delta x. Let's go ahead and expand this out. Is everybody cool with that? All right, when we expand all of that out, 7 plus delta x, let's do it right here. 7 plus delta x, this thing squared, is going to be equal to 49 plus 14 delta x plus delta x squared. We're going to plug this back in now. We're going to get the limit as delta x goes to 0 of 49 plus 14 delta x squared plus, my bad, 14 times delta x plus delta x squared minus plus 3 minus 49 plus 3 all divided by delta x. So distribute this -3 because they suck and they're negative. I don't know, I didn't have a good joke for that. When we do that, everything is in these set of parentheses becomes -49 minus 3, right? So now we can drop the square bracket parentheses. Agreed? Let's do that. Well, hey, this is going to cancel with this 49, right? This -3 is going to cancel with this +3. And what we're left with now is the limit as delta x goes to 0 of 14 delta x plus delta x squared over delta x. So hey, in our numerator, we can pull out a delta x. When we do that, turns into this, right? All I did is factor out a delta x. But now, our denominator can cancel out with that delta x in our numerator. Everybody cool with this? What we're left with, we come back over to Kate, is the limit as delta x approaches 0 of 14 plus delta x. 4 plus 14.
How are you able to tell that from, like, without doing all of that?
Yeah, what was my cheat, right?
Right.
How did I get there? How did I know that right off? I'll never tell. I did cheat. And we're going to talk about it in our future class. The way I was able to do that, we will get to. There's a set of rules that we can use to make all of this easier for ourselves. But before we get there, I want y'all to see the monotony of doing it the long way. And I want y'all to do this by hand so many times your hand cramps up and you hate it. Because when that happens and we get to the properties, the shortcuts, the rules, you'll commit it to memory right away. You won't fight it. You'll be like, dope, let's do this, because I hated that stuff. Makes sense what I mean? Yes, ma'am.
Where does the delta x go when we find 14?
Yeah, where did it go? So let's go back to this. All right, I'm going to keep this. I'm going to move it up. So this purple left us with the limit as delta x approaches 0 of 14 delta x plus delta x squared over delta x. And I said, hey, this term and this term both have a delta x, so let's factor that out. That's going to give us the limit is delta x goes to 0 of 14 plus delta x, that quantity times delta x, divided by delta x. This and this will cancel now. What we're left with is delta x goes to 0, 14 plus delta x. Make sense? Yeah. So what do y'all think? Am I gonna say this yet for making you have to do this hand by hand over and over and over and over again? It's gonna suck, right? Good. I wanted to. That way, like I said, when it gets to the other parts, you'll be more inclined to commit it to memory. You'll be more inclined to appreciate where we came from to where we're getting to. This way, it'll motivate you to actually take the time to understand and memorize it. Because ain't nobody got time for that. Having said that, with 3 minutes left, I will let y'all go.
What is our exam?
Oh, yeah, that reminds me. Thank you for reminding me. The exam will be the end of next week. I'm still working out some of the details because obviously we've now lost 2 days for the snow because of technical problems, effectively 2 other days. Like we've almost lost a week and a half, 2 weeks. We're about a week behind the schedule, so I'm trying to work out, like you said, some of the details of how I'm going to make the exams available to y'all. But they will be at the end of next week. And they will be on WebAssign. Having said that, I'll stick around if anybody has any questions.